paper usually belongs to a major research in which we are so
Hello.
Okay, good morning, everyone. Thank you very much, Armando, for the nice introduction. I will start here today saying that it's a great honor for being here today to present this part of our research for you. I was reading the list of participants in this meeting, and probably I already read papers from most of you, so it's a great pleasure for being here today. And this title, From Hertz to Megahertz, it explains a little bit about the history of our research in Brazil, at least the research that I have had the chance to participate and to contribute. So a brief agenda. I will start with an introduction on Inverter-Based Resource. It's probably not new for most of you. Maybe for all of you it is not new, but since I will try to present the history of learnings that we have here. So the introduction will consist of a basic explanation about Inverter-Based Resource and the features of IBR that can affect protection functions. And then I pass for a second part of the presentation in which I will explain the lessons learned in recent years. And when I say from Hertz, it's because we look at that fundamental component sometime, but recently we are looking toward the transient, so the megahertz is the context of this analysis, especially regarding the traveling waves, the traveling wave based functions. And then I will finish the presentation with some final remarks, presenting some context in Brazil, how we have dealt with these problems, and some news. My first contact with this topic took place in 2018, when the first meeting of a CIGRE group, the B5.65 group, took place in the University of Brasilia, where I worked for 7 years. And at that opportunity, at the first moment, I was very excited. So I said, okay, let's go. It's very nice. Let's talk about protections applied to IBR interconnecting lines. But few moments after, I could realize that I have a lot of questions in my mind. What are IBRs? And if protections are affected, why IBRs must be used, or why protection functions are affected when IBRs are close to that scheme, to these schemes of protection, and what are the operational features of IBR that affect protections. I realized that I had a lot of why in my mind. And at that time, as soon as the meeting finished, I talked with some colleagues and I asked them about where to start, how we can start to study this topic and to better understand the problem, because we use it to understand source as an equivalent, a Thevenin equivalent, and now things seems to be different. So where to start? And we decided to start understanding the IBR connection and the basic principles of these IBRs. So in my learning, understanding the operation modes of photovoltaic power plants and wind turbine generators, it was probably the most important part in this learning. Basically, we know that photovoltaic panels induce DC voltages, whereas wind turbines will generate some AC components with frequencies different from the nominal frequency. And at that time, we understood quickly that these components should be converted to a DC format, extracting the maximum power from this primary source of energy, which is like mechanical in the case of wind or from the radiance and temperature. So we understood very well this part of the IBR. But this other part here, from the capacitor until the system, was a little bit confusing for us at that time, until we understood that there is a balance between the input power and the exit power, which is controlled by such a voltage across the capacitor. And we understood that by controlling this voltage within specific levels, one can guarantee that the power is transferred from the primary source until the system. So once we understood that, we decided to analyze different IBRs. There are some people that say that when we are talking about wind turbines or photovoltaic power plants, we are talking about what they call IBS, like inverter-based source, because IBRs would encompass battery energy storage systems. But I use the term IBR here. I think that there is no problem in doing that. And at that time, some years ago, our first contact with the IBRs was with the type 3 of a wind turbine generator, which is the doubly fed induction generator. We had to understand that the generator has two paths of connection with the grid. The first one is through the stator, and the second one, we have here a rotor windings connected via converter until the grid. And if we consider now the two converter type, there is some differences. And this was a very interesting learning because in the first moment, we were thinking that all IBRs would be the same thing. But after some study and taking some material from the literature, we could realize that there are differences. And in this case, the full converter is completely decoupled from the grid, since it has only one path of connection. It is very similar to the photovoltaic topology, but the difference is that the first converter here is not an AC-DC, but rather, when we consider the PV plants, we have DC-DC-AC converter. But in our case, if you see the second stage of these converters, we have a DC to AC converter, which are the inverters. And the question here is how these inverters are controlled and how they can affect protection functions or even fault location functions. We noticed that there is a low inertia because these generators do not have huge mass to maintain an operation points, and the mechanical time constants were replaced by the control time constants, which are much faster than the mechanical ones. We understood that there is a low inertia to deal with. And due to these particular connections, we realized that particular control strategies and behaviors during faults were also an aspect important to be understood. So, looking deeper into the inverter, we just noticed that these switches have a very simple function to reconstruct the AC characteristics of the signals, which are placed here across the capacitor. I mean, the voltage across this capacitor must be inverted by these inverters. And here we can see that these voltages that take place here at the terminal of the inverter, they can vary in between plus and minus 2/30 of the voltage across the capacitor. But these voltages are not exactly a sine wave, so that we have to use a low-pass filter, and so we can see the grid voltages, which are the filtered versions of these these signals at the inverter terminals. If you see here, when one can realize that the currents that are injected into the electrical power system, they are proportional to the voltage across this filter and the filter characteristics. So this filter has an important task on this model, such that we have to pay attention on that. But the main characteristics when we decided to analyze the inverters was related to the current levels. We read in several papers and books that currents must be limited here because otherwise this switch can present problems. So the limited currents during faults are explained. A lot of people think that the limited currents are only related to control schemes, but this is not completely true. Some IBRs have currents limited by the limiters that are applied to protect the switches. Just to demonstrate such a behavior of voltages and the importance of the filter, I modeled by myself here a very simple model in ATP draw of an inverter. There is a very simplified pulse width modulation scheme here and some switches. I disregarded the generator, but I replaced it just by a DC source, which is emulating the voltage that is provided to this capacitor. And here we will measure the voltages at the inverter terminal and the grid terminal after the filter. And here the power grid is being emulated by Thevenin equivalent circuit. And here there is a load as well. These are the signals that we obtain by making this model, by simulating this system. These are the voltage from the phase to the ground measured at the inverter terminal. And to demonstrate you the importance of these filters, I decided to implement two types of filters which I took from the literature. And here we can see that different distortions can take place in these signals. Regarding the amplitude, these amplitudes can also be different. It will depend on these filters. So distorted signals can take place in IBR outputs. This was another learning that we had at that time. After that, in 2019, I decided to invite a master student to help me in these studies. I was a beginner in the topic, and so Jonathan is the name of the student. He started to make some simulations using EMTP, and in the first paper that we published, just a very simple paper to start the works, we could see that the currents measured from a full converter-based wind power plant here, when we vary the fault distance, we could see that the currents were indeed limited, whereas the currents measured at the power network terminal, they vary proportionally to the fault distance. I mean, inversely proportionally for faults that occur closer to the terminal, the current increase, but this logic is not followed by currents at the wind farm side, on the wind farm side. And a very similar behavior in voltage was noticed, but this behavior was, a little bit more easy to follow, because there is a slight variation here in the voltage levels at the voltage measured at the wind farm terminal when the fault position was changed. And the same thing was verified in the power network side. However, the voltages here are much smaller than those verified at the power network side. So We concluded that limited currents and very low voltage levels during faults are expected in this type of system. It was a 30 learning. Then, once we understood these aspects, we received the news that a report, an IEEE report, at that time was released in 2018, and it was addressing the impact of IBRs on both power system dynamics and short circuit performance. Grid following technologies, which basically take the grid voltage information to synthesize currents that are injected to the system. They basically can be represented by current source, and most of the early control schemes only inject positive sequence currents, suppressing the negative currents and disregarding voltage support. It was an important information for us because we could start to understand some protection problems that were found at that time. And more recently, we could see that another standard from IEEE, which is the IEEE 2800 standard, and this standard was written in partnership of several experts. Some of them are present here today. I think some of them are here. People from universities and other companies collaborated to build this document. And this is very interesting because this new standard, basically, it leads us to think different. It was inspired, actually, it was inspired in the VDE grid code from Germany, which was already programmed to inject reactive current for a grid support, voltage support. But it is now also including the negative sequence current injection. So grid following technologies are still seen as current source, but there are different components which are injected in order to improve the behavior of protection and the behavior of the system as a whole. So, motivated by the releasing of such a new standard, we published recently a paper in the Electric Power System Research on the benefits of such a standard for transmission line protection. And one of my preferred figures in this paper is this one, where we make an overview, we provide an overview about the early grid codes and the innovations which are taken into account in the new standard, which are in red color. And here we can see that there is a grid code voltage support, which is provided by means of a controlled reference of the reactive current, what we call reactive current. And here, there is also a negative current injection, which is triggered when the fault is detected. So when a fault is detected, these two control loops, they interact and they are summed here, and then they control the pulse generation, which will control the IBR. And this is a very important aspect that I will explain better in the next slides. But there is another element in this scheme which I consider that is like a heart of the IBR, which is and this element is the PLL, the phase locked loop. The PLL is responsible to measure the magnitudes from the system and to estimate the frequency from the system, to take it as a reference to synthesize the current that will be injected in the system. But if such an input voltage which is taken from the grid, which is very low, PLL may present problems. And if the PLL present problems, these frequencies can be erroneously estimated. So we may face some frequency deviations, which are a problem for protection functions. This is why the voltage support element here is very important, because as soon as we inject a reactive current, voltages remain at a certain level that guarantee a good operation of the PLL. So these frequency deviations are reduced, and as a consequence, the impacts and protection schemes are also reduced. This problem, the problem of frequency deviations on distance protection elements. The first time that I read about such a problem was in this paper, which was written by Bogdan. And this is a very nice paper, in my opinion. I had good times reading this paper. And he was very clear in the explanations when he said that there is a rotating trajectory that can take place here depending on the fault resistance and the frequency deviation between the contributions that come from the IBR and from the grid. In this paper, he proposed also some new operating characteristics, including what he called as weakening feed distance element. And to see this problem, but we decided to put it in a paper, to write some notes, and to study the problem to better understand it. And basically, we could verify that, okay, if the fault is established through a resistance, an almost pure resistance, so a real value, we have an in-feed effect such that for a fault here inside zone 1, for instance, for a distance protection element, the loop impedance is supposed to travel until here, but this real element here will move the impedance toward the right side, and then we have another element will move a little bit more this impedance to the right side with an angle. But due to the frequency deviation, this element here is not a constant. And this is why the rotating characteristic takes place here. And when we understood the message of this paper written by Bogdan, we realized that there is a problem that is difficult to predict. At least in our opinion, it's difficult to predict, because if we have an internal fault and this impedance is supposed to take place here, but it is moved toward the right side and here, and if a rotating characteristic takes place, we start with an underreach problem, and after some time, depending on this rotating characteristic, the impedance will take place inside the operation zone. So we start as a erroneous operation, and then we become a correct operation. It's interesting, but in the case of external fault, the impedance is supposed to take place here. It is moved toward the right side, and if our rotating characteristic takes place, we start with a correct operation, but if this impedance travels here, it can enter the operating characteristic, so the protection can present a malfunction. So it is difficult to predict. So underreach and overreach problems can take place. And this is why voltage grid support is important to reduce the frequency deviation. This was our conclusion, because by guaranteeing that voltage grid support is operating as expected, the frequency deviation will be reduced, and so these rotating characteristics will be also reduced. And I will demonstrate some case that we verified such a behavior through ATP simulations. Another aspect that I have seen and that has been widely commented in the literature, it regards the doubly fed induction generator in units, and it is related to the chroma operation. We know that if in fault case, there are some high currents that may flow through the rotor, and thus this rotor connection here through the converter may establish high currents through the switch, which is not good. Thus, the crowbar has the function to short circuit such a converter in such a way that when the crowbar operates, the doubly-fed induction generator becomes a simple induction generator. If we analyze the current during faults in an induction generator, this expression would be representative. But we have to know that induction generators usually operate with small slips, which are of about 1 to 2% percentage. But in doubly fed induction generator, high slips can take place because the converter corrects the quantities, and thus appropriate quantities delivered to the grid. The problem can take place when we have a high slip and the crowbar operates, because we can see in this case an induction generator that will start at least instantaneously soon after the crowbar operation with a relevant frequency variation. In some papers in the literature, some authors report deviations of about 20 hertz in 60 hertz systems. So this is a problem. We know that there is a limit to disconnect the generator and the system depending on the frequency variation, but at least in a transient manner, it can be a problem. So there is an uncertainty regarding the crowbar operation, and this is a critical uncertainty. So this is in this slide, I present the last part of the first findings and learnings that we should have before starting the lessons learned. Fact, for a long time, when we started to study this topic, a lot of colleagues asking me about, okay, I think that we will have problems whenever we have IBRs connected to the grid. And I was wondering about that, and I tried to understand some things. And my conclusion is that we are trained to think in a complex manner sometimes. And the conclusion was, okay, it depends. And it depends on the IBR current flowing path, obviously. And it is a very simple concept. But at that moment, when everyone was concerned about the problem that IBR could pose on protection schemes, it was very enlightening for me. And basically, this is a traditional topology of connection. Here we have IBRs. They can be wind turbines or photovoltaic panels. Here the strings. There is a medium voltage feeder connecting these IBRs until a collector substation. Then there is an interconnecting line, which is the main subject of our studies, and then the point of interconnection. Some people say that this point of interconnection is here together with the collector substation, but just for the sake of simplicity, I am considering that the point of interconnection is here. And there are some very illustrative scenarios that I can comment here. The first one is that when a fault takes place outside the protected line, for instance, let us assume that this line here is the protected line. It can have problems because through this line in this case, only the IBR contribution will pass through it. But these adjacent lines here, if there is a grid contribution which superposes the IBR contribution, then the grid is usually stronger than the IBR most times. So here it is not expected to have a problem. But if the grid is disconnected or a weak grid is considered, the IBR contribution will pass through both lines. And we started to understand that the problems are not limited to the interconnecting line, but rather they can reach the adjacent system. And so far, we don't know how much lines can be affected from this contribution, but we know that adjacent lines can be affected. I mean, the protection schemes applied in adjacent lines. So this is a problem, an important problem, but it depends on the connection topology, obviously, and the connection topology is equally important if we compare with the atypical behavior of IBR. So understanding the topology is crucial to understand some problems. The same is verified when we consider an internal fault. In this case, there is a contribution which comes from the grid, and another contribution which comes from the IBR. So if we consider the measurements from both sides, current measurements, if we are talking about grid following technologies, the problems may appear at one side, but they may not be observed in the grid side. And this aspect, this behavior, it can be expanded to understand some behaviors that are related to modern technologies, such as the traveling wave-based technologies. Because if I want to protect this line, considering traveling waves, I have to measure traveling waves at the IBR side, on the IBR side, and also on the grid side. But these terminations have different characteristics. So the IBR terminal may present problems, while the grid terminal can properly operate. But even using transients, and we know that transients do not depend on the IBR controls, even using transients, understanding the termination is very important. So this was the first part of our lessons learned, and thus now I can just emphasize that we are looking so far much more to the grid following technologies, which are the most used here in Brazil. We know that grid forming are coming soon, and there are some research and applications. The grid following now, they can change their operation mode to be grid forming depending on the way they are connected. We know that as well. But our studies have focused on grid following so far, although we intend to expand the studies to grid forming as soon as possible. So the lesson one was blind zones on the interconnecting line may exist if communication is lost. It is not a new information, and it generated a paper which we presented in the DPSP in Liverpool. There we were evaluating real devices, and we are considering some protection functions from the perspective of operating number of operations and operating times. In this paper, basically, we took into consideration a traditional interconnection system. Like here, we have the power network at the right side, and here the IBR connection. This is a very long line, in my opinion. We considered some busbar capacitances, which will be addressed soon in this presentation. And two scenarios were taken into account. The first one is with communication channel, and the second one without communication channel. And 4 real relays from different manufacturers were taken into account, considering distance protection, phase elements of the available differential protection, pilot schemes, and whenever the weakening fit logic is available, we activated the weakening fit logic. It resulted in 120 internal fault scenarios in which we varied the fault features. And we could see here that the differential and pilot schemes operated with a very good performance, but the distance element was very affected, especially at the bus L, the local bus where the IBR was connected. And in this sense, we prepared a figure to demonstrate how much coverage we could have in each case when communication channel is available and without communication channel. And at that time, we could conclude that there is a blind zone close to the IBR in which the protections can simply not operate even if the fault is inside the system. In this situation, we noticed that the importance of backup protection. Obviously, we know that backup protection is always important, but in this case, backup protection is even more important because the protections can simply be blind to the event. Then we have the lesson 2. The typical IBR fault contributions are not limited to fault current levels. In the first studies we could participate, most people use it to say that we have problems because we have limited currents. And in the same real case, in the first real case that we opened the fault report, we could see that there was a huge overcurrent, but this is these are the magnitudes from voltage phase, sequence voltages, currents through the phase, and sequence currents, and here are the angles, the respective angles. And we could see that there is overcurrent here. So where's the limited current? So we started to understand that it depends on the fault, it depends on the system groundings, but we could see that there is a very relevant under voltage in the faulted phase, and that these currents here, they present the same angle which characterize the zero sequence contribution. So we understood that this contribution was coming from the system, not from the IBR. But there is a very interesting behavior here that can be noted, because low fault current contributions are only one of the possible impacts. We know that. But we noticed that in this real case, the angles were changing for some time, and then they stabilize. So we noticed that, okay, it's difficult to take a decision here because the control scheme is still converging to its final values, let's say like that. And we could face it for the first time, the need to wait the control scheme to stabilize. But another possibility was considered at that time, that opportunity, it was to quickly operate before the control starts to change, but considering other quantities rather than fundamental component. And at that time, we understood why a lot of people in Brazil who was using time delays in protection, and why the traveling wave technology gained an importance also in the context of IBR interconnection systems. And recently, it was confirmed in the IEEE standard when they write in the section, I think that is the F.6 in this standard, when they say that the underreaching element should be reliable when their settings consider the IBR response time, or when they write the control system of an IBR may need some response time. And also, use of supervisory overcurrent thresholds and time delays may improve protection system, or even backup protection may include application of time-delayed step distance zones. So we are talking about intentional delays, and people in Brazil is using a lot this recommendation. But we were curious about that, and we decided to analyze some cases using real device from different models, and we had the chance to model the early control strategies in which no reactive current and no negative sequence currents are injected. And then we adapted our models to represent the new standard. And we could see that the need for time delays, it doesn't disappear. Okay, because the first moment of the fault, there is a transient state of controls which leads. This is the angle comparator used to apply the distance protection. And there is a transient state that we have to wait, and then the controls stabilize. But depending on the control strategies, they can stabilize outside the operating characteristic or result in a very delayed operation. And in using the new standards, when we inject the reactive current and the negative sequence current, we can see that they stabilize inside the protection, the operating characteristic. These results are available in this paper that we published recently. So this is the second lesson, and the third lesson is pay attention to PLL and digital estimation filters. This is the case that I mentioned earlier to respond Fernando. We know that controls in grid following technologies, they need a frequency reference to synthesize the IBR terminal currents, and different PLLs can be used. And in a Brazilian paper, we do not have the English version so far of this paper, but basically we implemented two types of PLL, among which one of them is the one that most people say that is the best one, which is the DSOGI. In Brazil is DSOGI, like that. And when you consider the inverter switching maneuvers and the PLL operation, distorted phasors can take place. And when I say distorted phasors, I mean the signals may present some distortions with harmonics, interharmonics, but also frequency variations. And when we analyze these distorted signals for different phasor estimation algorithms using half-cycle windows and full-cycle windows, and considering different PLL models, we could see that the distance protection function can be relevantly affected, whereas the phase element of the differential function remained very good. So this is a combination between that distortions in the signals that I presented in the first slides, and also with the PLL operation, so we can have some problems like that. Besides the rotating characteristics that I have already mentioned. And these problems of distorted phasors, it was also addressed by Bogdan in the same paper that I mentioned some slides ago, when he says that one can calculate the operant impedance directly from the time, avoiding the phasor estimation. And indeed, it makes sense for us, because we could notice that avoiding such a problem of the filters used to obtain the phasors, the behavior is more stable. So it's important. The literature is already addressing such an aspect. So the lesson number 4 is, for each system, a particular study is required, so uncertainties are unavoidable. From the literature, we know also that topologies and control strategies can vary a lot, and uncertainties are unavoidable, especially regarding grid codes. We do not know exactly how manufacturers of wind turbines and photovoltaic power plants, how they are applying the grid codes, and the standards can help to reduce the problem that can take place on protection systems. The chroma operation and the sleeps at the chroma operation instance are also difficult to know. It's also difficult to predict. Converters have continuously been improved. I have the chance to participate in a meeting only on power electronics, and I was amazed in relation to the number of solutions that people from power electronics and power converters, the number of solutions that they can implement in practice. IBRs at multiple terminals are coming soon. We are starting to see some debates on that. The battery energy storage systems, among other questions that can result in uncertainties on the protection operation. In the last Paris session, 2022, we published a paper which is the inspiration of this presentation. The title is very similar to the title used to this presentation. Basically, here we demonstrate that two different grid codes can result for the same system in very different frequency variations depending only on the used control system, control strategies. Here, we took into consideration an American grid code which does not consider the reactive current injection, and the VDA from Germany, which is a European grid code, which considers the reactive current injection. And here, we can see that the variation in the frequency when we do not consider the reactive current injection is much greater than the one verified when the reactive current injection is performed. And what is the consequence of these differences? The consequence is basically that rotating characteristics, when we are focusing on the distance elements, that rotating characteristics due to frequency deviations, they change a lot when we consider the voltage grid support. And just for the sake of comparison, here is a scenario in which we are considering a conventional generator. We vary the fault point from faults inside the monitored line until external faults. Here is the grid code. When we consider the reactive current injection, we can see that there are some oscillations, but they are very reduced in comparison to the analyzed American grid code here that we considered in this paper, where we can see that rotating characteristic, it appears and it can be easily observed here. And another aspect is about it's related to the fault resistance, because what we expect is to see that as the fault resistance gets higher, we expect to see the loop impedance moving toward the right side. But depending on these control strategies, they can move down or toward the left side. So by changing the control strategies, trajectories change, and they also depend on fault resistance, is also a combined effect. And these trajectories are addressed in such a recent paper that we published. I have already mentioned it. Basically, here we are testing internal faults and external faults. We can see that for internal faults, there is, for some resistance values, when we consider the early control strategies without reactive current injection, and neither a negative sequence current injection, there are some directionality problems that can take place here. And if an external fault takes place, we may lose selectivity here. So the trajectories change by changing the control strategies. But when we consider the new standard from IEEE 2800, we notice that the behavior is very, very closer to the traditional one. So these loop impedances, they move toward the right side with some angle, exactly as we were used to see in traditional systems. So the behavior of IBRs approach the traditional one if we consider the new standard, which includes the reactive current injection and the negative sequence current injection. Just for the sake of demonstration, we tested also some phase selection functions, including those that consider current analysis, we know obviously since there is a suppression of negative sequence current, for instance, in the early control strategies, it was already expected to have only erroneous results. I mean, because the phase selection simply do not occur because the thresholds of minimal negative sequence current, they are not respected here. But when we consider the new standard, since it injects some value of negative sequence current, this minimum threshold is respected, the condition is met, and the performance of current-based phase selection functions, it is improved. Thus, we know that there are already some voltage-based phase selection function. It is, and we have to recognize that this is a trend when we are talking about IBRs. It's much more reliable to use voltage in this case. But by considering this standard, the current-based ones are improved and they start to work as expected in most cases. This is the problem that I mentioned about the uncertainty regarding the chroma. Just to illustrate a paper that was published by Professor Ali Houchia, one of the first papers we read, and it shows that if that sleep is high and the chroma operates, the loop impedance can travel over the plane, so this is a problem. And from these results, we can conclude that EMTP modules are especially important when we are studying IBRs because these phenomena can only be observed during transient simulations. So it is difficult to conclude some of these problems, to verify and to test some of these problems if we consider phasor-based simulations, for instance. And it was a topic addressed in the last Power System Computation Conference that took place in Porto, Portugal. And I saw a lot of research groups around the world saying that, okay, let's use EMTP to evaluate that because other programs usually do not reproduce properly the events. So this is a problem. So EMTP is very important in this type of study. So the lesson 5, not everything is control, but the interconnection circuit topology matters. Basically here, what we know is that zero sequence contribution comes from the system and it returns through the grounding points. And this is not a characteristic of the control. People for a long time were believing that these problems, this alignment between the three-phase currents were related to the IBR controls, and they are not related to the IBR controls. They are related to the circuit topology. And this is very important to understand that we can have overcurrents and that the zero sequence elements are still very reliable in this type of system when this contribution has a path to flow and to enter again here in the line. Okay. But such an aspect, it can be extended to the traveling wave problem, because traveling wave problem, the traveling waves are inherently incremental quantities, as you know, and they do not depend on the fundamental components, except by the fact that the amplitude is defined by the voltage point on the wave when the fault takes place on the line. But you have to remember that when a fault takes place and the traveling waves are launched, the termination will dictate if this wave will be reflected with an opposite sign or with the same sign. Since here we have a transformer terminated line, for current traveling waves, there is a -1 reflection coefficient for current traveling waves. So what we expect to measure here is nothing. But when we consider voltage traveling waves, there is a voltage reflection coefficient equal to 1. So the amplitude is amplified here. And in this sense, this is a problem of transformer-terminated lines rather than any IBR influence. And we started to investigate such a question, especially from the aspect of testing relays using simulated data. So a careful modeling is recommended, especially of line terminations. And this is why we had the lesson 6, where we say that EMTP models must include stray capacitances, because depending on the stray capacitances at the busbar and across the transformer, voltages and currents may completely change their behavior from a transient perspective. And in this case, we can see in these figures here, currents without the busbar stray capacitance, we have almost nothing in terms of transients, but when the busbar capacitance is included, the transients take place. And the opposite behavior is verified regarding voltage transients. So this is an important aspect. And in September 2021, we published a paper in the Spring Journal in which we demonstrate that there is a minimum value of busbar capacitance that must exist to guarantee the sensitivity of traveling wave elements. But at the same time, we could perform some studies in real systems, and we could observe that most systems have sufficient busbar capacitance to guarantee the sensitivity of traveling wave functions. Obviously, it depends on the system, but it was a very interesting evidence that we can use traveling waves in these systems, even having a transformer terminated line. So in this paper, we demonstrated that including in simulations, for instance, the stray capacitance would not affect phasor-based functions, which were available in relay 2 and 3, relay 2, 1, 2, and 3 here for distance functions. But for traveling wave functions, it was a mandatory modeling strategy, because if you disregard the stray capacitances, it will conclude that traveling wave-based functions will not operate in that system. And this is, in my opinion, at least in my opinion, this is an erroneous conclusion. It depends on the system, so you have to analyze the stray capacitance, and perhaps you can use traveling waves in a reliable way. Basically, here we have a real record, and we can see that there is a wave here reaching the IBR terminal. So the traveling wave, this is a transformer terminated line. So if the traveling wave can be measured, so we can conclude that this stray capacitance exists. This is a recommendation that we have said to people here in Brazil. You can use traveling wave, but before that, maybe it would be interesting to analyze the levels of the stray capacitances at the busbar and across the transformer. 1 month later, only 1 month of difference, the paper Traveling Wave Current, a new way to protect lines terminated on transformers, which was written by Bogdan and Venkat and Stefan and Ralph Baroni, was published, and we were very happy to see that you guys that are involved with the relay manufacturer and developing solutions for real-world systems, you are thinking the same line. And this element here, we are already studying, and in my opinion, it's very promising. So this is a very recent paper, which is to be released next week. It will be released in the Electric Power System Research Journal as well. And in this paper, we assess some traveling wave functions in inverter-based resource interconnecting lines. We studied a lot the variation of these capacitances here, and we implemented different traveling wave-based protection elements as well as fault location elements. And we took into consideration a typical interconnection system, but varying these capacitance around the transformer and at the bus bar, at the local bus, which is connecting the IBRs. And this figure here is basically the signals filtered by the differentiated multi-filter. The terminal, the local terminal is the IBR side, and the remote terminal is the grid side. We can see that on the IBR side there is some additional oscillatory behavior in the differentiated multi-filter outputs due to the transformer characteristic, but at the grid terminal, the expected triangular or parabolic shape output is obtained. But there is an interesting behavior here, because as soon as the reflections reach the IBR and go back to the remote terminal, they start to distort also the reflection. So detecting reflection here is very difficult. These signals here are related to the fault point F1, which is an eternal fault. And considering now a fault behind the transformer at this point here, F2, we can see that the wavefronts are very distorted. So this oscillatory behavior may put into risk some detections, but the good news is that the amplitude of these signals is very low. And it was explained in that paper that you published in October 2021, and it was confirmed through these studies here using our models. And basically, these levels here are not enough to sensitize the travel wave elements that we were analyzing in this paper. So these additional oscillations are observed, and they are a point of attention, and they occur basically due to the termination influence, which is a transformer. So a summary of the conclusion in this paper regarding the differential travel wave based elements, it correctly restrained for the evaluated external faults. The case of low stray capacitances led the scheme to lose sensitivity, which is expected because the amplitude is reduced of the induced travel wave, so the security conditions will block the function. The distortions in the measured travel waves are a point of attention, as I mentioned earlier, especially for external faults on the grid side. But the used conditions guaranteed the security, especially regarding the amplitude of the waves. The directional element based on travel waves was also tested, and we considered the implementation available in this paper here from NIAC, because this element, it considered current travel waves, but instead of using voltage travel waves, it considered a pre-fault voltage signal, and by doing so, it can overcome some difficulties due to the capacitive voltage transformer that may reduce the transient content in the signals. And this element presented an overall good performance. It properly distinguished forward from reverse faults, but low stray capacitances also affected the decisions at the IBR terminal, especially due to current travel wave attenuation, which is also expected. We implemented also the overcurrent element based on travel wave, and it showed to be very promising. And just for verification, it was studied also at the IBR terminal. It presented an overall good performance for higher stray capacitance at the IBR terminal. We know that the original application do not consider the application of such a function at the IBR terminal, but we are interested to see how much critical would be the function if it's applied at the IBR terminal. And it presented an overall good performance, but low stray capacitances reduced the scheme sensitivity at the IBR terminal as expected. But in our case, this element presented a good security, which led us to think about, okay, maybe the overcurrent element with the directional element could be a solution for the blind zones that protecting the line from the IBR terminal without the need for communications. But this is a question to be answered after further investigations. And finally, regarding the travel-based fault location methods, we tried to apply both double-ended and single-ended methods, but the double-ended presented better results because detecting the reflections after the distortions caused by the transformer at the IBR terminal, detecting the reflection is a little bit difficult. So the double-ended method showed to be quite reliable and accurate, so accurate as it has been in traditional systems, but the threshold used to detect the wavefronts is undoubtedly a point of attention that must be taken into account. So, as a final remark, I would like to say that some utilities in Brazil, they have adopted new protection strategies, but in my opinion, it's a very personal opinion, innovations are still scarce in Brazil. Protection engineers have tried to solve the problems caused by IBRs, mainly considering delayed operations, which is okay. It is mentioned in the new standard. It is possible, and they have accomplished the fault clearance within the time required by the TSO. But in Brazil, there is a discussion in progress with regard the fault clearance time. Today in Brazil, the fault clearance time is equal to 100 milliseconds, but the transmission system operator is wondering about reducing it from 100 milliseconds to 70 milliseconds. And in a recent event that I was participating, I could talk with some colleagues from Brazilian utilities, and they said, I don't know what I will do if they reduce the time, because we are applying delayed operations in most systems with IBRs. So this is a practice, but this is an interesting context that I want to share with you here in Brazil. And they also solve the problems counting on unit protection. Usually the differential protection elements, they have been considered mandatory in new projects which consider the interconnection of IBRs. And I usually say that they also count on their own luck, because there are a minor part of people that thinks that there are no problems. Even knowing that a lot of people, a lot of research and professionals are investigating this topic. Despite that, I have to say that there is always a great concern about the possible problems that IBRs can cause, especially because in Brazil, the renewable resources are increasing a lot. If we sum wind generation plus photovoltaic IBRs, we have a percentage of participation in the generation in Brazil of about 16.9%, and we are expecting to increase it to about 22%. In my opinion, considering the huge size of Brazil and of the interconnected system, is a great participation in the generation. And we have seen that incorrect tripping commands have started to appear, and they are increasing in number. This is why the Brazilian TSO has just changed the grid codes. The grid code here were not, they had no requirement to inject reactive current, neither a negative sequence current, but now in Brazil, the reactive current injection is required by the TSO. It is new in Brazil. And I think that in the near future, they will adopt the injection of negative sequence quantity, because the new standard from IEEE has shown it to be quite beneficial for existing protection systems. especially because it leads the IBR to approach its behavior to the high inertial units. And finally, as trends and future opportunities, I would say that non-unit protection that can be applied at the IBR terminal are very welcome. I still believe that this is a need and that we are in the correct way to find something like that, because we could reduce the dependence on the communication channel and we could avoid blind zones, guaranteeing a proper operation in short time windows. But this is a topic that has been widely studied. I think that is opportunity of development. Regarding the travel-based applications, they have gained more and more space in Brazil. I have the expectation to see this application expanding here and in other countries as well. But specifically here in Brazil, I do believe that the use of travel waves in this type of system will be associated with the decisions from the TSO regarding the minimum fault clearance time. The maximum fault clearance time. Because the travel waves are the solution that required to be faster, but people is still using time delays. And depending on the decisions from the TSO, maybe the travel waves can gain more space, even more space in the market. And so we know that there are a lot of issues to be investigated, including the influence of battery energy storage systems, multi-terminal IBRs, the grid forming, the hybrid power plants when they combine wind turbines with photovoltaic power plants and BESS. So we have various topics to study and challenge to deal with. And this is my final message here. I would like to thank the various research partners that have worked with me. And on these guys, Moises is an amazing student in this area, and Professor Mario Lescovis has been a great partner in this area. So I would like to thank all of them, especially Moises and Professor Mario, for the support and for the learnings and for the discussions. And I'm sorry, I think that I passed some time from my limit, but now I can respond to questions if you have. Thank you very much for your attention.